one to here? Sweet, all right.
You could also have hair on our screens.
Yeah, I don't like doing that, it's weird. I'm just slowly with technology, right? I'm old. Sorry. Okay, so basically, what we're going to do is we're going to start with counting and show you how counting can be used, that the algorithm of counting, the process we do for counting, how that can basically be used to create conversion into other bases. So it sounds really sort of intimidating at first. People are like, oh, you're going to convert from this base to that base. I remember my brother tried to teach it to me. He's just like, you will come to that, you know. And I was like, oh my God, I don't get it. But it really is pretty easy. So I've got this little, this is the expanded form method. And this is basically counting and you don't realize it. This is a nice representation of how we count. You just don't realize it yet. And then after that, we have the multiply and add algorithm for both the integral part and the fractional part. And then if you want to go, these are all from base B into decimal. So binary into decimal, hexadecimal into decimal, octal into decimal, etc. If you want to go the other way, from decimal into something else, we have this one. So what do I mean by decimal? Does anyone know?
Base 10.
Base 10, right. So that's what we work in. We work in base 10, mostly. Okay, so you'll probably want to use that as we get into this a little bit. But before we do that, let's talk about exactly what we do when we count. And what I'm interested in mostly are its application to sets. So when we count, so I'm trying to go, really want to go this way. No, I don't. I really want to go this way. Okay, sorry. When we count, like let's say we're working in some sort of base 4, right? Or base 5. Base 5 is nice. I can never remember what base 5 is.
1, 0, 1, 2.
It's quanta.
Quintal? It's quintal.
I want to think it's quintal, but I always get that wrong.
That's in the book.
Okay. Anyway, so if we go to base 5, we don't. When we count, we have we start with basically 0, and we're 1, 2, 3, 4, and we can go to 5. When we hit 6, what happens?
0, 0. Shift.
Which shifts. We take this group of, you can look at it two different ways. We can take this group or this group, but basically we take this group here, and we say I now have one set. Oh, anyone else? Attendance? I now have one set of 5, right? I have one set of 5. So I put that one set of 5 over here into the now 5's column, because it's 1's column, 10's column, 100's column. Now it's 1's column, 5 columns, etc. So yeah, thank you. You saw my brain lock, did you? That was awesome. I went, I don't know. Okay. So we take one unit of 5, one set of 5 over here, and we come back and just wipe that out and start again. Right? Does that look weird? Looks really weird to me. Yeah. That's weird. Never mind. 1, 2, 3, 4, 5. We have another set of 5. So we take this set over here. We now have 2 sets of 5. Right? We do this on and on until we get 3, 4, 5 sets of 5. When we're done with that, what happens? On our next, after we count 5 one more time, we now take this set, and we have one more set of 5 to put over here. What happens?
We create a set that includes the second set.
We create a set of sets of units. Does that make sense? So really, the reason I bring this up is, and I'll harp on this because your book does it in a weird way, when you're borrowing, you're not borrowing 1. Do not borrow 1. You're borrowing a set of your radix. Oh my God, there's a word. You're borrowing a set of your radix. What's the radix? Anyone? Math people?
It's just another word for the base.
Base. The radix here I'm working in, radix or base, EX, EX, IX. Yep, radix or base, same thing. Right now my radix is 5, right? So that's what I'm working in. So right now we're working in, say, 5, base, 5, whatever. So when I'm borrowing a set, right? So if I'm doing some sort of subtraction in base 5, and I have, like, say, 14, I'm going to call it 14, and I'm going to say minus, let's do that as 13 minus 4, right? I need to borrow from here. I'm not borrowing 1. What am I borrowing? 5. So if I cross this out and make that a 5, right? And then 3 plus 5 is what?
8. Wait, what?
Yeah.
No, you crossed out the 3, not the 1.
Yeah, I know. Thank you. But 3 plus 5 is 8. 8 minus 4 is 4, right? So that's what we're doing. And we'll go over that again later. I just want you to understand why we're going over counting, because it's like, why are we going over counting? That's the first thing we get from counting, is we understand that we're actually borrowing a set. You're not borrowing a 1. This makes binary really easy, because your book, he will tell you to borrow 1, and then he'll send you to these charts that say that this minus this and that plus that is this, and you have to memorize the charts. I hate memorizing things. Forget it. I'm not going to do it. But if I know that I'm in binary and I've got 1, 0, and I'm minusing 1 from that, he will tell you to do this and then borrow the 1, and then he'll send you to a chart. Well, forget that. That's ridiculous. I'm borrowing a set of what?
1. 2.
My radix is 2. I'm borrowing a set of 2. 2 plus 0 is 0. 2 minus 1 is 1. That's the difference between those numbers. Right? And we'll go over this again. When we get, this is part of we'll go over this again. But this is what we're learning here. This is why this is counting. This is why counting actually works. Another thing that counting gives you is the idea of the expanded form. This is the ones column, right? With base 5. This is the,
5's going.
why is it the 5's column?
Because you borrowed a set of 5.
Because I borrowed a set of 5. So really I have 5, 5 to the 1, 5 to the first. Right? Because I have 5 raised to the power, each one is a set of 5. 1, 2, 3, 4, 5. 5 to the first. Each one is a set of 5.
Well, provided we're reading from the left. Yes.
I know, I'm backwards. I realize I'm backwards. That's why it's looking really weird to me. I don't know why but at any rate. Over here, once I get to this side, once I get to this column, so if this is 0, this is 5, this is, why?
5 squared.
5 times 5 is 25.
Because I have
Yeah, 5 squared.
a set of 5, and I apologize, sorry, I never learned to write like this. So for those of you on this side of the room, I deeply apologize. You're supposed to be able to write this way, and I can't. It's horrifying. But I have and then, so here, I have one set of 5 of 5s. I have a set of sets of 5, of 1s, right? So it's 5 squared. Okay, so what's the next one? 5 to the third, 5 to the fourth, 5 to the fifth. So what we're dealing with here is we're into the expanded notion for a number. So if I give you, this by the way is the place value.
I just wanted to make sure I'm understanding. So the only time 0 comes into place is the first set?
Right, sorry, thank you. Awesome, my bad. Anything raised to the power of 0 is what?
1.
So it's our units column. So if I have 1 times 5 to the 0 is 1. If I have 3 times 5 to the 0, so this equals 1, this equals 3, because it's 3 times 1. Right? So that's what we're doing. I'm moving very quickly, I apologize. I'm going to slow down because I'm watching people go like, wait, what? So this is our place value. So let's do this. 1, 2, 3, 4, 5. I don't have any digits past 5 in this space, so I'm stuck. So, or not stuck, I'm done with this column. This is equal to 1 times 5 to the 0, which is equal to 1 times 1. This is equal to 1 times 5, oops, wow, goodness. 2 times 5 to the 0, which is equal to 2 times 1. 3 times 5 to the 0, which is equal to 3 times 1. 4 times 5 to the 0, which is equal to 4 times 1. And 5 times 5 to the 0, which is equal to 5 times 1, right? It's our units column, because we're only dealing with groups of 1. We're dealing with single units. Over here, in our 5s column, a unit here, or I want to not call them units because it's somewhat confusing, but an entry here is equal to 1 times 5 to the 1, which is equal to what? 5. Or 1 times 5, which is equal to 5. I'm running out of. 2 times 5 to the 1, which is equal to 2 times 5. 10, yeah, that's right. And then 3 is 3 times 5 to the first, which is equal to 3 times 5, which is equal to 50. Yeah, I can't even count in 5s today. I'm doing really well. Christmas was long. Just saying. 4 times 5 to the 1 is equal to 4 times 5, which is equal to 20. And 5 times 5 to the first is equal to 5 times 5, which is 25. Okay? Let me move this slightly. 5 to the second, an entry here.
I've got questions.
Oh, sorry, what's up?
Oh, no, I was just thinking at the beginning of every set, though, do you have like a 0 times thing? Which would
Yeah, 0 times anything is 0, so we just leave it as 0.
Yeah.
Yeah.
So, okay. I
And-
was just assuming that.
No, it's a good question. Hold on one second. I'm gonna right back to that.
Yeah, that was my question too, because my understanding is that we count the 0 first, and that.
So 0 is fascinating, and if you ever want to read a really great history of 0, is it called is it the Magic of Phi? I'll look it up. I have it at home. It's a book. But this mathematician writes this book on it. He goes into the history of 0 and where it comes about. Because 0 is actually fairly late in our counting systems. The Egyptians worked really well, built amazing pyramids without 0. Not a clue. I don't believe they had 0. But it comes about through the Sumerians, who would initially start with a period, a dot, as a placeholder. So 0 is really a placeholder. What 0 says is that I have nothing in this set, but there is a placeholder here. That I know that this set is in existence, but I have nothing there. So 0 kind of is and isn't, and it's a really, really odd number. And I'll show you why that gets really wonky in a minute.
So why in the book does it say the final unit in the base has to be one less than the base? So the book, it says that 5 is not part of the base 5. It only goes to 4.
Am I working in base 6?
I think you might be working on base 6.
Yeah, I think I'm working in base 6. Christmas was long.
Just take away the 5. And
Yeah, sorry. Yeah, thank you. My bad. I was wondering. Okay, sorry.
I was confused.
Sorry, yeah, Christmas is base 6. Okay, sorry. Yeah, that works better. I did that when I bobbled over it and I circled it. I was saying you can include the 0 or not. I got it right in the video, so apologize. Yeah. So I just lost like half of you. Just went, wait, what?
No, I get it. 'Cause
Does anyone not get what I just did and not get just?
I get how to explain it. So
Yeah.
if you add 0, you've got 5 numbers.
Right, that's why when I circled it, I was like, wait, what?
So,
That's just my first clue that I'd gone overboard.
so the best way to understand it is, even though we're not talking about 0, we go 0 times 5
Right.
is 0 equals.
So if we have 0 as a placeholder, we actually have a unit of 5 when we get to the next one.
Right.
Or we can say at the next drop. And the way I do it in the video is at the next count, this magical non-existent 5, which doesn't really exist, becomes our 5th set and moves over here. So that just gets picked up and moved over here. So when we come down here, this non-existent 5th set of sets gets picked up and moved over here. So I apologize. I'm just apparently 11 o'clock still too early.
It's early in the morning.
It's too early
It's
for
very
this.
early.
Yeah. Okay.
Computers
So,
start at 0, so
and we'll talk about that. Yeah, zero counting becomes a major part of your life here. And again, if that doesn't make sense, like, just throw stuff at me. If I'm going too fast, throw something at me. What can't you throw?
Paper.
bananas.
No, he knows. He knows. Because I had him before. I've had him in other classes. No Furbies. Anything but a Furby. Furby has a hard beak. Could put my eye out. But no, just my point is, if I'm going too fast, say something, because I talk really, really quickly, and I have to try to teach myself to slow down. Okay. So here we have 1 times 5 to the second is, 1 is 1 times 5 to the second, which is equal times 1 times 25, which is equal to 25. 2 is 2 times 5 to the second, which is equal to 2 times 25. And I'm going to lose it here very quickly.
50.
It is, yeah, 50. Okay. I'm not very good at adding, subtracting, multiplying, and dividing. Theoretical math, no problems. But and you can use a calculator for your monkey math, by the way. I don't care. That's why they exist. That's it. And I won't ask you to memorize large bits in this world. We live in a reference world, and in programming, when you go out to the field, you're not asked to memorize. When I took C, I had to memorize everything. We don't live in that world anymore.
A good way to help yourself when it comes to the binaries and different bases is to use the computer calculator on Windows.
Yeah, we'll get to that. Yeah, totally. So 3 is 3 times 5 to the second. Does everyone get the process here, basically? What we're doing? Does this make sense? This is the expanded form. Okay? Yep.
So this may be because the book explains it poorly.
No, it's because I do. Go ahead.
No, this is maybe jumping a bit, but I got the sense that expanded form kind of loses its usefulness once you get past the superscript of the base. Since I didn't notice that you could say if a base 5 number has 6 digits, I didn't see that you could expand it.
Well,
just keep
you
going?
can. No, so what happens, that's the same mistake I made. A base 5 number shouldn't have 6 digits. It should have, oh, I see what you mean, 6 digits this way.
Yes.
No, it's fine. You just keep going. You can just keep going ad infinitum.
Okay,
It's
so
fine.
I can go up to like 5 to the 25th if
Yeah.
I so want. Okay.
Yeah, if you want to make the calculation of some number, some unit times 5 to the 3,467th place, that's fine. I mean, your calculator's going to love you, but whatever. It's not the calculator's position to gripe. It's the calculator's job to do its job. Okay. So if we take base 5 and we have 1, 3, 4, 2. This is our number in base 5. How do we put that in expanded form? What does that basically equal?
1 times 5 to the third times 3 times 5 to the second times 4 times
1
5.
times 5. So our base here is 5. 1 times 5 to the 0 position, the 1 position, the 2 position, the 3 position.
Other way.
Other way.
Well, you want us to read from the left or the right?
1,342.
Oh my God. 0, 1.
There you go.
Sorry. Jesus, Louise. Okay. Yeah, sorry. I don't know why I'm. Okay, it's like several times today with this.
First day class.
It's confusing.
No, it's. Yeah. Anyway, so 2. So we have 2 times 5 to the 0, right? Because this is our lowest spot. See, I was basically Egyptian in the last life, so I read this way. And I don't do vowels either, so it's okay. This is what? 4 times 5 to the first, right? This is 3 times 5 to the second. This is 1 times 5 to the third, okay? So this is equal to 2, and these are added together. Again, I apologize, I'll step back for those of you over here. This is added together, these are added together. So this is 4 times 5 this is 3 times 25, and this should be 125? Yeah. 1 times 125. So this is 125 plus 3 times 25 is 75 plus 75 plus 20 plus 2. Adding those together, you get 22.
122.
What is it?
242. What? No, it's 222.
This is our base 10 equivalent of that number. You have just converted to base 10 in the easiest possible way. You've taken base 5 and made it into base 10. Very cool, right? Like, yay, I can do it. Woo. And you get up to the pearly gates and you can present this and they'll say, good for you. Right? You can also try to present this at Starbucks and you're going to get pretty much the same response. Good for you. This is very useful in computing, though, because computers work in different bases. Computers work in binary, some base 5, but not really anymore. Binary, hexadecimal, and octal. So base 1, or base 2, base 8, and base 16. And we'll get into base 16, which is really funny.
Base 12 in the homework is fun.
Right? Yeah, no, totally.
Is that excluding byte sizes?
No, that's actually the typical collection of bytes into of bits into bytes and how they usually come at us. Yeah.
So everything that I've learned up to this point, which is starting in the computer world,
Right.
I have been functioning in base 10.
Yes, because humans are base 10 creatures. Why are humans base 10 creatures? Anyone? Anyone? Yes. We have 10 fingers. Right? That's why we're base 10 creatures. Just for giggles and trivia, why is it always first, second, third, and everything after that is TH? Fourth, fifth, sixth, seventh. In every language. First, second, third. Always different. Well, in most every language. I know like 4, but not well. I'm illiterate in 4 additional languages. Why do you think first, second, third? It's really weird. It's just they're just it's the first it's the same reason we have your to be verbs are always different because it's really primary. The 1, 2, and 3 were our first counting numbers basically. First, second, and third people in a row or whatever. We never went beyond that for a long time. Is his theory. Anyway, neither here nor there. But the reason.
You can hold something and you can still count where you're holding something.
Yeah, basically, or that could be that sort of thing. But the reason you've been working base 10 with everything is because the computer's been doing the work for you in other bases, and we'll get to that. And the reason the computer's doing the work in other bases is it's first off binary because stuff is just on and off. Which, by the way, does anyone?
Just because I always thought it was a dash and a circle.
No, it's
No.
It's the state. Well, it's more complicated than on and off. It's the state.
Well,
Yeah.
it's the transistor.
Yeah.
Basically, it's
But it gets
active or
more
not.
different than that. It gets more interesting than that. Quantum computing. Anyone familiar with it?
Yep.
So what's happening with quantum computing?
Well, it depends on what you mean.
So basically, you split it. Oh, go ahead.
Yeah, you're basically splitting the two different actions together in 1 and 0, and quantum computing is basically based off both 1 and 0 as the answer.
Sort of. I take a particle and I split it, and the two particles A and B go that way. If I destroy A, what happens to B?
Nothing.
Oh no, it goes away.
Yeah.
But they
Much
also,
to the chagrin of every physicist in the world, particle B just decides to no longer exist. Because particle A is destroyed, particle B is destroyed. I now have a situation of particle A exists, it is on. Particle A is destroyed, it is 0. I translate that across time and space somehow. Particle B exists, particle B is no longer exists. I now have an on-off state. I can do computing
don't they have-
instantly through what is more or less subspace for all you Star Trek freaks. Stand up and be proud. No, what?
But there's other things they're doing where they're going like the state. They can do over under voltage depending on
Yeah.
how they're holding it, and that's
Right.
like a trinary computer.
Yeah. And I'm not terribly familiar with that. I just I remember reading about this and being very excited about the idea of instant computing over any distance. But the point being, computers are operated on a state of basically on or off, for lack of just to be simplified about it. And then that gives us binary. We can take binary, convert it to base 10. Let's do that. So what you've been experiencing is basically this. If I'm working on a binary number, right? 1011. It's my favorite number. What is the value of this in expanded form?
That would be 1 to the 1 times 2 to the third.
Nope, this way. I did the same thing I did.
Oh, okay.
Same thing I did.
1 times 2 to the 0 times 1 times 2 to the first
1 times 2 to the 0
plus 1 times 2 to the first plus 1 times 2 to the third.
which is just 0. You can just put a 0 in there, I don't care. But just for giggles, 1 times, or 0 times 2 to the second plus 1 times 2 to the third, right, like this. So this is equal to what?
That's equal to
4. 1 times 4.
8.
Oh.
1, 2, 4, 8.
Oh, my bad.
It doubles the, yeah, no, I do that all the time. So 1 times 8 plus 0 to anything, or actually 0 times 0, or 1, 2, 4, plus 0, or 1, 1 and 2, because 2 to the first is 2, plus 1 times 1, right? Taking this gives us 8 plus 4 plus 2. Thank you. Plus 1.
That's 11.
Not quite 8. Yeah, it is. Okay. I'm sorry. Yep. No.
Hey, I'm confused.
My-
Is the 4 supposed to be
My
that
favorite
one?
number is 1101. That's my favorite number. Anyways, what?
Oh, I see. Never mind.
Did you get it? Okay, yeah, so this is 0 times 4, so it's 0, and I did the same thing. I do it frequently. So 8 plus 2 is 10 plus 1 equals 11. So this is the binary equivalent of 11. So the computer, every time you enter an 11 and do something with it, it's basically doing this with it. And we'll correct that sort of egregious generalization later on in the next section. But this is basically what it's doing with it. So, does that make sense? Binary? Cool. Place value. Place value in binary is really super simple. We've kind of been dealing with it. And I'm going to show you. Oh, God, I didn't bring it. Find mine. Okay. We don't have to go through this. We really don't have to go through this. Your author kind of talks about this a little bit. But the place value for binary, and I'll see if I can put this in the right order. Yes?
I'm sorry. Okay,
Go ahead.
so I understand this. How does the base play a part in that?
Well,
Like base
because
value?
what we're doing when we're counting in binary, and let me count in the proper order this way this time. I start off with nothing. I add 1. My enumeration for binary, if my rate x is 2 for binary, my enumerations are 0 and 1. This is my enumeration. And an enumeration, by the way, I asked this. Who used to have this thing in the Army? I stomped, but I'm just going to check. I asked this on the exams. An enumeration is an ordered set. I also have it in the video. I go over it. This set, it is a set. It's complete. There's nothing beyond it. So it is a complete set. And I count from order 0 to 1. I don't count 1 to 0. So it is an ordered complete set. It is an enumeration. You'll get used to the word enum. How many taking intro to programming this quarter? Right, you'll get to enums very shortly. Right? So that's where it comes from. It's an ordered set, a complete and ordered set. So our enum here is 0 and 1. These are the only digits we can work with. So I start at 0. I count 1. My next count for 2 doesn't exist. So what happens to it?
You carry it over.
I bundle it up, and I now have one set of 2, and I start again. Count up, count again. My next drop, I don't have a 2, so I bundle that set up, right? That 2 up, move it over here. but I don't have a 2 here, so I have to bundle up another set of sets of 2 and move it over here. Right? So I know I'm within the grounds of your question. I'm trying to get back to exactly what your question was, which is how does this play within the 5? You can see it's basically the same thing. That I'm just doing sets of 2 or sets of 5 or sets of 10 in my
What determines that?
the base. That's what I'm saying. My base here is 2. Let's see.
The ordered set contains the radix starting at 0 and
Right.
0 times.
So let's do this. 1 second, Shari. I'll get.
Oh, I was just thinking of an example.
Oh, okay.
So if you did a really long binary, would it go from like 0, 1, and then it would start back over?
Yes.
Yeah.
Kind of, but what I want to get to it for
No, I'm thinking that would be an answer to her question.
well, what I'm hearing for her question is this: if my radix is 2, my enumeration set is 0 and 1. Wow. 0 and 1. If my radix is 5, my enumeration is 0, 1, 1, 2, 3, and 4. If my radix is 8, my enumeration, of course, is 0, 1, 2, 3, 4, 5, 6, 7. If my enumeration is 10, what would it be? 0 through 9. And I'm holding off on 16 because it gets a bit weird. We'll go to that in a moment. Does this make sense for how the base happens? The base here is 2, the base here is 5, the base here is 8. That's how we get that base. And it's a very good question. Thank you.
Yeah, 'cause that didn't make sense to me either. I was like, because we had shorter binaries and it was always just the going
Yeah.
through the same exact sequence. But I could see how that'd be different if we were going through a longer thing. It would.
Well,
not-
let's just,
it would
okay.
be the same.
For giggles, since you all seem to have a fair grip on this, everyone not have a fair grip on this, kind of, okay, maybe. All right. So if my radix is 16, no, really. If my radix is 16, he does 12 in the book. 16 is much more common. We call this, quintal, I think. Binary, quintal, octal, hexadecimal. If my base is 16, well, it's pretty easy at first. 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens next?
A, B, C, D.
We didn't have anywhere to go. So the council called me, the IEEE called me, and they said, James, man. No, they don't. They don't call me for anything. I made that joke in the video. So you're like, you don't have any fresh jokes, do you? I'm like, no, I don't. No. It's easier that way. If I just recycle the same stuff over and over, I don't have to memorize anything. So A, B, C, D, E, and F. Yeah. Just have to stop and think about that. 11, 12, 13, 14, 15. No. 10, 11, 12, 13, 14, 15. Thank you. Yeah, every time with that. I'll do that every time. So will you. By the way, that's why I do half credit or partial credits on your exams. You get a point for attempting, you get a point for going in the right direction, and you get a point for getting there. In pretty much everything I grade, with exception some of the labs sometimes they'll split that into 2 parts, just because if there's no real path sort of thing. It's like, but you get partial credit at least for trying always, because there's a lot of moments here that are really easy for little slip-ups, and I do it all the time too, and my hypocrisy has certain bounds. Yes.
What happens if you go through the entire alphabet? Like, what do they use, like A, B, B, or something like that?
Well, they do, but it works out really nicely. You'll see later. Because you can divide each of those up into a 4-bit piece, and then it makes sense, and you'll be able to recognize, like, F is always this set.
And yeah, and for the most part,
What?
we don't really do that a whole lot. The Sumerians worked in base 60. That's about the closest you get to that. I don't think we have any number systems that we really work with that are that long. I'm sure someone has done it, and at that point in time, when you start doing stuff like that, you get to dictate. And I can do anything for a radix, for an enumeration. If I have, if my enumeration, my base, let's go, my radix for giggles, is my special mystical radix, I'm just going to call it. And it consists of star, square, diamond, and circle, right? How do I count in this?
Star, square, diamond, circle.
So if I start out with star, I then go square, I then go diamond, I then go circle. What happens on my next drop? I bundle that all over as a set of here, and that starts over. And I'm going the wrong way again.
You're forgetting about your placeholder though, which has to also exist.
See, and that's what I was talking. That's what actually screwed me up last quarter. Is I got halfway through this, and I'm like, in the lab, I'm like, oh god, my placeholder. So this has to be 0.
Right.
This has to be my placeholder. So you can say that I begin with, in all of my columns, some star. That's a star, trust me. Some star, and then I add to it that,
There you go.
that, and that. When I get my next drop, these go away, and I get a square over here. And I then start again.
And they're all to the first power.
And these are all to the first power, 0 power, first power, second power, third power. So it doesn't matter what your digits are. These are nonsensical. These are arbitrary, really. They're what we decided to use. Yeah.
I'm just trying to wrap my mind around.
Okay,
the
let's keep.
multiplication of. Like, I don't even want to
Oh.
think about that. But the letters and the math of
Oh,
letters. Does
okay,
that just get very
sure.
algebraic?
Let's do this.
or-
No, let's do this. Let's say you have
Sure. Why not?
1C, A, whatever, and a base 16 number, right? This is a 1. You know it's a 1 because I doesn't exist in here, nor does L. So what's my expanded form of this?
So you just don't come up with like an answer. There's no
10
way.
plus 11 plus 1.
Right.
This, right? This is basically, we can say that this is A times 16 to the 0.
Yeah.
And we'll get to it. I'm getting there. I know what you're asking. This is what?
Okay. So that's yeah.
C times 16 to the second.
Yeah.
And this is 1 times 16
To the
second. My God. First to the second. Yeah, thank you.
Okay.
Okay. What is A worth, basically, in 10? You just have to remember this. Which is why, by the way, you were talking about the number systems. This is where it becomes very complicated, right? Because you have to remember that A here is worth 10. In a number system like you're talking about where you're on to ZZ, you'd have to remember what the base 10 value of ZZ is in order to do this, so it gets kind of wonky. So A is basically worth 10, right? 10, 11, 12, 13, 14, 15.
Sorry.
So,
Light bulb. Okay. Oh.
yeah. No, it's good. I like the O sounds. It makes me...
Yeah.
15 times 16 to
It's
the
just a
0.
placeholder because the computer can't
10.
10.
Wow, what is wrong with me today? Oh my God. Okay.
Okay, I know.
And so C is 10, 11, 12.
Just because the computer can't 10.
Right. Times 16 to the first. And this is 1 times 16 to the second. And you
And
can
then
see
you can
where we
solve
can
it.
just keep going, right?
Yeah.
Then we just take 10 times 1, which is 10. We take 16 to the first, so 12 times 16.
192.
100 and what? 92?
I think so.
Ish, somewhere around there. And then 1 times 16 to the second, which is 30.
I don't
No,
know.
no. What is 16? 256? Right, 256. Like that.
Yeah.
So you can just convert it that way. And by the way, you can see why I let you do, I can't even do basic. Arithmetic in my head and mathematics in my head, it's not going to work.
And your answer is 458.
What is it?
458.
458 is the decimal equivalent of 1 CA. Right?
That's a life knowledge that we're going to need.
I know, because see, again, you can take this to Starbucks and with $3.75 you can have a small coffee.
And the other way,
But that is how you convert using the expanded method. Does that sort of make sense? Yeah.
Yes, makes sense. So,
But there's always a but.
What?
so the reason that we do this is because a computer does not operate in tens, 50s,
Correct.
right?
And
So the computer would
Um, yeah, and you're actually, and it's fine. I'm gonna address it slightly. No, but you're into the next section, which is cool. I'm glad that you're there, because you're like me. You want to know why that is, so you can understand why this is. And in fact, when I was in my warrant officer basic course, no, yeah, I was. A guy in this corner of the room, he stood up and goes, "Look, just give me," and he looked right at me. He's like, "Just give me the formula." And he's talking to the instructor, but he's looking at me. "Just give me the formula. I don't want to know," and I'll plug in the numbers. I don't want to know why. Because I'm that way. I'm always like, why does it work? How does it work? If I know this, I can bring it in and do things with it. And so I'm a big fan of knowledge hooks. So, with that in mind, what happens? Does everyone have this? I can get rid of this. Okay. So to look ahead in the next section slightly, when computing first comes about, like we said, it's all in ones and zeros, right? So back to this place value of decimal, place value of binary, sorry. Place value of binary is 1, 2, 4, 8, right? It's a beautiful little program. I'll put up an announcement that will allow you to do this. It's a game that teaches you this. So if I have a 1 here, a 0 here, a 1 here, and a 1 here, what's my value of this?
1.
What's my value of this?
0.
What's my value of this?
4.
My value of this? 8. For a total of?
13.
That's my favorite number. For a total of 13. This is the way the computer thinks. Note that we have 8. Nice, right? 1 to 1. Boom. Really simple. I can just assign a place value here. I don't have to do any calculations at all. In fact, that's what this whole little game I'll post teaches you. And I gave it to my kid, and he beat it. My kid beats everything. It's really weird. It's freaky. He's like, "Oh, that's easy." He gave it back to me. I'm like, okay. But basically, it just puts up numbers here. What's that number?
9.
And you can do that without looking hardly, right? Because it's 1 plus 8. Because of what we call our place value here. Because of our place value, we know that we have an 8 value here and a 1 value here. Really easy for computers to think in base 8. Super duper easy. The conversion, of course, from base 8 to base 16, right? You can already sort of see that because 8 into 16 is just a doubling. And if I add 8, I'm going to make sure that that's right. 2, 4, 8, 16, 32, 64, 128, 256. Do these numbers look familiar?
Bit numbers.
Yeah. But why does my memory always come in 256? Why can't I get like 12? Right? You know, and it's because of these registers, these binary groupings that we work in, which is why base 8 and base 16 are so prominent in computing science. Because they're just really easy to work with. And as we get to this, we'll see that converting over between them is super, super easy.
Yeah, that's
Base 10 is the hardest one for a computer to deal with, frankly. It's really weird.
wasting a lot of space.
Yeah, it does. Base 10 sucks. and yeah. So, all right.
So
Does-
is it going into that you convert the 4-digit binary into each of the values in the radix 16, right? That's because the total length of a 4-bit byte is 16. Well, 15.
Right.
Well, 0. It has 16 word sets.
Right, yeah,
Right.
yeah, yes.
And so if you look at the radix 16, the 0 through F, every time you see that
Right.
4-bit byte, you can just go, this is 0 through F. Okay. So that's F.
Let's see, 0, 1 for our place value. 0, 1, 2, 3. Oh, wow. Yeah, let's do it, sorry. 1, 2, 4, 8, 16, 32, 64, 128. Care to venture a guess what the 10th value of that is?
What?
15.
15?
No, I'm sorry. There's a direct relationship between these 8.
Right. So I just draw a line down the middle between each of the sets.
I think I
And
got
then just
this.
go,
But
the one on the right is F, and the one on the left is also F.
I'm really lost.
hold on a second. Let's deal with that afterwards. I kind of know where you're going, and I don't want to get to it just yet. Yes? See, and that's why I don't want to get to it just yet. There is a happy little relationship here between this 8 set and the other 2. So before we get to that, we've got just enough time to go over the other method, and we'll get, because this really, we are really jumping into section 3.
I think we're there.
Section 2. Yeah, we're really very close. I know, we've just been all over it, which is fine because this applies to that, so we're building this scaffolding up slowly. All right. Yeah, we haven't done the fractional part yet, so we haven't done this. The fractional part of any base, if we're going from base B to decimal. So if I have, let's go back to our base 5 for a second. Let's go back to our base 5. And we take a number of 12.31, right? So we've done this. This is 1 times 5 to the what? 0, 1, yep. Plus 2 times 5 to the 0. Plus 3 times what?
5 minus 1.
5 to the negative 1. So this is 0, 1, 2, 3, negative 1, negative 2, negative 3, right? On out. So what is 5 to the negative 1? 5 to the negative 1. Which is 1 over 5. Which is what? 0.2. Should be 0.2. Please tell me it's 0.2. Should be 0.2. Please, God, tell me it's 0.2.
Think about it.
Oh, no, sorry. No, just 1 over 5 itself. My bad, sorry. So it's just, I want to take the decimal equivalent of this 1 over 5. 0.2. So, sorry, okay, yes. I know what you're saying. So 3 times 0.2, right? Yeah, we'll get to that. So the next one is plus 1 times 5 to the negative 2. 5 to the negative 2 is, of course, 1 over what? 1 over 25. And 1 over 25 is 0.008, right? No. 0.04. Yeah, right. Plus, so 1 times 0.004. Or 0.4. Man, doing this today. 0.4. Yep. Right? So that's the way you do this. So then you can just kind of get rid of these here. You can replace these here with this right down here. So you add this up. 1 times 5, of course, is 5. 1 times 5 is the first 5. 1 times 5. 2 times 1, because 5 to the 0 is 1. So 2 times 1 is 2. 3 times 0.2 is 0.6. Plus 1 times 0.04 is 0.04. Add those up, and you have your number again, right? So and that's all we got. We have the same thing right here. 0.2, 0.3, 0.2, 0.4, 0.008. So you do the integral part over here and the fractional part over here, and you just put them together, and you've got your fractional equivalent as well. Does that make sense? Cool. All right. The adding, and multiplication algorithm of it, the multiply and add algorithm, sorry, basically works like this. The thing to remember here is that in your integral part, you're going to work this way, and your fractional part, you're going to work this way, which is really, really wonky, weird. There's some calculator tricks, which I think I'll show you tomorrow. We'll see if we get to it, on how to do this very quickly. But we start off to work this number through. Let's go ahead and work this one. 2044.403. 2044.403 in base 5. This one? You like this one better?
I don't like it better. I like the other one better, but it was easier to grasp quickly.
The other one or this one?
This one, because it's just 2 things repeating themselves.
Yeah, basically. So to start with the integral part, we go ahead and take our first number at 2, and we multiply it by our base. 2 times 5 is 10. We then add our next number. So that one's here. We then add our next number. Plus 0 is 10. We then multiply that by 5. 10 times 5 is 50. Yeah. Yeah, okay, got that right.
How do we multiply something by 4 and get 10?
You don't.
It replaces it.
It adds in. It adds in. So basically we take the 0, we added a 0 to this because there was nothing in that place. So now we're going to add in a 4 into this number, because when it multiplies, we're going to multiply that grouping of 4 here by 5. So we add in the group, we add in the set for multiplication, we then multiply by that set, is kind of what's happening. So we have 54, I'm going to move this back up here. So we have 54, we multiply that by 5, and 5 times 4, thank you, 220.
I'm wrong.
Okay. 270. We then add in our 4 for 274, multiply that by 5, and we should come up to our,
Just leave the last
no,
one.
that's it.
The last one.
That's the last one. Once we add in the last one, we're done. Because we're adding, why when we add in the last one are we not multiplying by 5? Because it's the units column. Yeah, because it's the 0 power, it's the units column, so I don't need to multiply it by 5. It's the last one I'm done. I'm adding in my 1s for my final group. So that's 274 for that. Here, the trick is to go in reverse, and you'll note that we're multiplying by what? By this 1 over 5 again. So we're taking the base in the negative, we're taking 1 over the base, is what we're multiplying in for the fractional parts. So we're multiplying in 0.2 in this case. So we take 3 times 0.2, which is 0.6. We then take, and it's actually 0.6, and I want this 0, right?
Replace.
Yeah, I want that 0. And then I take down the 6 down here, and I multiply in that by 0.2. And that gives me, of course, 0.12. Yeah, I then add 4 to that. Oh, I'm sorry. This 0 gets added in here, 0.6. Now I'm going to add the 4 in here for 4.12. Multiply that by 0.2. And you come up with 0.824, like that. Apologize for doing that really weird. We'll do more of those.
How does this make logical sense? Like, how did someone come up with this?
Because there are people in the world who just don't have a social life. No. Yeah, it is really weird. But basically, if you look at it, here we're multiplying by our base, right? And on the fractional part, because we're multiplying by fractions of the base, we're actually multiplying by 1 over the base because everything over here is -1. So we're just taking this, multiply the first number times that. We then take the second number, and we're basically adding it in again, right? So
That's the part I'm.
we're still adding it in. So, okay.
So what happens if you end on the last term and it's a multiply instead of an add? So say instead of it being a 4-digit number, it's a 5-digit number.
Oh, it still works. Let's do it. Does everyone have this? Where did this? We've still got like 5 minutes, so let's do this. Let's take, just for giggles, some base 5 number of 0.2481. No, can't do that. 2431, right? And I want to convert this to base 10 using this method. I don't have to worry about the integral part because we just did 0, so we're done with that. So working with this algorithm, what's the first thing I do? This. So I take this 1, and we're still working in base 5. So 1 times 0.2, which is 0.2. I then add in the 3. 3.2 times 0.2 is what? 0.64. Okay. I then add in the 4. right? Following that? So then add in the 4. So 4.64, right? And I'm just going to move this up here, by the way. 4.64 times 0.2 is what? 0.928.
Let's go with it.
Okay. So 0.928, I then add in my 2, right? Which basically, and that's what I'm doing. I guess that's the answer to your question is by putting in 2.928, what I'm really doing here at this stage is I'm taking 0.928 and I'm adding in 2. That's what I'm doing. So I'm really doing the same thing here. I'm adding in my next 1
Yeah, I understand
for the set part.
process. Why does that logically?
So if on the last term you had to multiply,
You won't.
that's still gonna be okay?
You won't.
You don't.
You'll never have to multiply because this is my last term here. I added in my 2. I multiply that by 0.5. Oh, I know what your question is. Hold on. I know what your question is. Let's finish this. So I'm 0.2, which is what?
There we go.
So 1.52, yeah.
What is it? 586?
Yeah, it's 5856.
5856? The decimal will always fall here. Is that your question? The decimal will always fall here. You'll never get a whole number here because, and he tries to explain this in the book, and frankly, I didn't really much get it myself either. But basically, you're working with tens of, so you'll never get more than your base out of it. Or not tens of, you're working with fractions of, so you'll never get more than your base out of it.
Another way I see how I work with it is I take the decimals and I get rid of them, but I count how many decimal places there were to the right. So the 2.928, there was 3 decimal
Be
places.
really careful with things like that because that can bite you very, very quickly if you start dropping things. Yeah, sometimes it's easier to do math that way, but sometimes you can lose your place and all of a sudden you're like, oh my gosh, I'm in the land of the headhunters and they're about to eat me. So, what's up?
Where did the positive 2 come from?
Here,
But
I'm adding it right in here.
How did it turn into?
this is
How did
my
it turn into
question.
the positive 2?
Like what?
Basically, because if you add it in as a fractional part, you're not.
But it is.
Yeah, I don't really honestly. I don't have an awesome explanation for that.
I get.
I will see if I can find an awesome explanation for that for you.
The reason
But-
it works is because you're multiplying by the set. So if
Yeah.
you add it in there, you're multiplying by the set.
And that's what I was gonna say. It's not a whole lot of help, I don't think.
Are
But
we
yeah,
gonna-
you're multiplying by the sets. But why isn't the sets a fractional part? And why is it when you move it? Why does the fractional part of sets work out to a positive number on the other side? And I don't really have an answer for that. I'd have to play with it or ask a friend. But basically, it does get back to the fact that you are working with sets again.
Because when you say you're adding the 2, you're really multiplying the 2 times the 10th column.
Okay, there you go. When you're adding the 2, you're multiplying 2 times the 10th column, right?
There we go.
So it becomes a positive, right?
Right.
Yeah.
And
That's why it moves on the other side. Thank you.
Because the next
Yeah.
step is a fraction, it's fine to have
But-
that number. Yeah.
Point being, you can use this on your exams. You can use this at home. You can use this out in the field. When you get out into the world, frankly, you just log on to the internet somewhere and you type in a number, and it gives you the conversion for you, anyways. So this idea of understanding that only happens in like when the nanites come out and disrupt all power. And we no longer have computing, which is a wonderful little sci-fi show. Okay. Any questions about this?
But that is the same thing as what we did the other way, right?
Basically,
Can-
yeah.
Will we have to do both methods?
Yes, on your homework, please do both methods, but you may use this sheet. Just get used to doing it is all I want. I want you to sort of play with it and you will develop an understanding of it. Maybe not a deep understanding of it, but you will develop an acquaintance with it by doing it over and over. Practice, adjustment, practice, assessment, adjustment, and repractice. And I do want you to do both sides so you can. So work each problem both ways in the homework, please. Cool. All right. Well, we will see you tomorrow. And we probably should finish enough time to do the lab tomorrow. So.
The other method makes logical sense.
It does.
But this one is just like you're grabbing into the napkin here and pulling something out.